Okay, well, welcome to the afternoon session of the opening workshop. It's my pleasure to introduce Daniel Fuentes-Keuthan from Johns Hopkins University. He'll be telling us about Goodwillie towers of infinity categories and desuspension.
Yeah, so first off, thanks for inviting me. I'm really excited to be able to talk to so many people at once. I guess also people I would never get a chance to speak to if it wasn't over Zoom. So there's maybe one benefit. Yeah, so today I want to talk about a little bit about Goodwillie calculus and some relation to cogroup objects and how you can use this relation to answer some classical problems. So maybe just start with some Goodwillie calculus. I think unlike most Goodwillie calculus talks, I'm happy to black box most of this because I won't use any particulars later on. But maybe just to give like a 1 sentence overview. So this is a field that tries to interpolate between stable homotopy theory and unstable homotopy theory. So stable homotopy theory via kind of polynomial functors. So if I think of stable homotopy theory as being linear, then and unstable homotopy theory as being very general, then I try to interpolate between some kind of polynomial functors, or as they're called, n-excisive functors, where n is the degree of the polynomial. So linear here is 1 excisive. And so the way this works, classically, Goodwillie introduces for a functor a tower of functors and natural transformations between them that sort of capture this approximation. So for example, if I have the identity functor on topological spaces, then I introduce a family of functors. Let's call it P1, one top, P2, one top. And the great thing about being on a Zoom is I can move things around when I don't give myself any space. And I have these natural transformations that go like this. And I have this tower here. And this tower is supposed to interpolate. So on the base here, this P1 of one top is actually equivalent to just infinite loops, infinite suspension. So this is the standard functor whose homotopy groups are stable homotopy groups. So there's the stable homotopy theory. And then on the top of this tower, if I call the limit of this tower, say P infinity of one top, then I'll use a double approximation as my weakest form of equivalence. This looks kind of like the identity on top, at least for certain spaces like nilpotent or weaker simply connected spaces. And so this tower interpolates between stable and unstable. And the idea is that whereas the bottom layer is supposed to be linear, as you go up, you get kind of more higher degree polynomials. This is a lot of times called the Taylor tower. It ends up looking a lot like Taylor series from normal calculus. In fact, if you wanted to look at, say, the layers of this tower, which is of course a very interesting thing to do. So let's say I have some functor, say it goes from topological spaces to topological spaces. And I defined DNF to be the fiber of the nth layer in this tower. Or when I talk about fibers, I'm talking about homotopy fibers. And I want to evaluate what this DNF is. So this is the difference between the n-1 approximation and the nth approximation. If I evaluate this on a space X, what this looks like is loops infinity. And then there's some spectrum that gets called the nth derivative of F. So this is some spectrum object with a sigma n action. Nice smash with an n-fold smash product of X. And now these things both have sigma n actions on them. So I can take orbits of that sigma n action, homotopy orbits. And so if you look at this, here's a derivative smash x to the n, and then you have to divide out by this n factorial. And so it looks a lot like normal calculus. So this is a big field, lots of results. that I'm going to step away from for a second and talk about a refinement of this to not just a filtration at the level of functors, but a filtration at the level of categories that Huyshoets develops in his thesis. So maybe specifically, I'm going to work with pointed, compactly generated infinity categories. And so maybe super brief description of each of these words. By pointed, I mean my categories have a 0 object. So something that is both initial and terminal, so like pointed spaces. By compactly generated, I mean generated from small data. So for example, how CW complexes are built by attaching cells. And by infinity categories, I just mean somewhere where I can do homotopy theory. So if you'd like to ignore all of these terms, you're free to assume that whenever I write a fancy script C, I mean topological spaces. But if you want maybe slightly more examples, I can take, so topological spaces, pointed topological spaces, spectra, or for example, O algebras and spectra for O some spectral operad, or other examples. Okay, so this is the setting that I'm working in. So what Heist does is attaches to one of these pointed compactly generated infinity categories a tower of infinity categories. So, and adjunctions between them. So on the base level, I have this adjunction whose right adjoint I'll call loops infinity 1, suspension infinity 1 is the left adjoint, and now there's P2C, P3C, etc. And I have these adjunctions, infinity 2, infinity 2, blah, 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 all the way up this tower. And the idea is that this tower of categories is supposed to be in the same sense that this tower for the identity functor here refined between stable and unstable homotopy theory in terms of this identity functor, just at the entire category level. So at the bottom here, this P1C, which should be like the linear approximation to C, is just spectrum objects in C. So the stabilization of C. So if C is topological spaces, this base level is just spectra. And this tower is integrated well with the more classical Goodwillie calculus. So for example, some key points, the identity functor on Pn of C is n excisive, so it's n polynomial. If I look at the induced map from Pn of the identity on C to this loops infinity n, sigma infinity n from the unit, then this is an equivalence. So if you want to think about the n equals 1 case, this says that the first excisive approximation of the identity functor on, say, topological spaces is just loops infinity, suspension infinity. And in a very precise sense that I won't spell out here, Pn of C is like the best approximation. So Heist defines what it means to be an excisive infinity category and what an excisive approximation should look like. And this PNC is the best one. It shares some factorization properties that extend the normal like factorization properties from linear functors. So for example, if I have f c to d is n excisive, then f will factor through the n excisive approximation to c in the same way that linear functors factor through spectra, for example. Okay, so this category PNC has a very explicit construction, and I'll go through this construction because this is the stuff that I'll actually use for the next 2 sections of this talk. So start with a big block of definitions that'll look familiar to people who are familiar with Goodwillie calculus. So these PNCs are built from the same kinds of cubical diagrams that show up all the time in Goodwillie calculus. So I'm gonna let box n square n be the n cube. So I can think of this as the power set on 0 through n. So set inclusion amongst these subsets give me the vertices of the cube and the edges. I'm going to let box n with a circle up there be the punctured n cube. So I take my n cube and I remove the initial vertex. When I talk about a cube or a punctured cube in an infinity category C, it's just a diagram, a cubical shaped diagram from either the cube or the punctured cube. I'll put a little brackets so that you can choose to be punctured if you'd like, into C. And the important definition, so I'm going to call a punctured cube special. So a very creative name here. Maybe a punctured cube is special if it satisfies the following two properties. So first of all the cardinality 1 vertices are 0 objects. So all the cardinality 1 vertices are is sent to a 0 object. And also for any two subsets S and S prime in this cube, punctured or otherwise, so whenever this makes sense, such that you can build the following square involving, let's see, can this appear on the screen? Yeah. Involving intersections here and unions. This is a push out. So I'll draw some pictures in a second. The second condition here, a lot of times is called strongly co-Cartesian. So that's what I mean by that. So the idea is I have a cubical diagram and every face in this cube that exists is a push out.
Daniel, can I interrupt with a question from Andrew Tonks? Do you want n cube or n plus 1 cube in this case, if you're indexing on the power set of 0 through n?
I want n cube. Am I off by 1 index?
It's just that it would be an n plus 1 dimensional cube if you draw it.
Yes, yeah, that is correct. Yeah, I probably want a n cube here. Yeah, so I probably want to go up to n minus 1. Yeah, the n should be the dimension of the picture that you draw. Okay, right, so to give some names to these categories of cubes, I'll call Tn of C the special punctured n plus 1 cubes, and Tn bar of C the special n plus 1 cubes. So there's that off by 1 dimension shift. So for examples of what I mean by these cubical diagrams, so if I take a special 3 cube, which lives in T2 bar of C, this looks like the following. I have some object. I extend it by zeros. So that was that condition 1. So all these cardinality 1 vertices are zeros. And then I have, I always get the indexing off here. Should probably be 0, 2. I have more objects here. And condition 2 tells me that every face in this cube is a push out. So there's a lot of push outs here. So that's what a special 3 cube looks like. You have some objects, then zeros, then you fill in the rest of the cube with push outs. A special punctured 3 cube, which lives in T2 of C. By the magic of Zoom, I can save time. Looks like this, where every face that exists in this diagram is a push out. So I think there's 3. So I'm missing this front face here. So it's just the faces that still exist are pushouts. Okay, so on the left, this is a special cube, and on the right, this is a special punctured cube. They look very similar, but it turns out that the special punctured cubes are much more interesting. In particular, the cube on the left is actually given by very little data. So there's a span. Starting from Tn bar of C, I can go to Tn of C by just forgetting the initial vertex. I can also get back down to C by evaluating at the initial vertex. And it turns out that this left-hand arrow here is actually a trivial fibration. So if you look at the cube up on the left, everything is really specified by this initial vertex here. So maybe in a very like hand-wavy way, once I pick this initial vertex, I'm just attaching some zeros. That's not adding any information. Because I've attached these zeros, saying that these squares are pushouts really tells me that all of these vertices are just suspensions of this original object. And so this last thing is just a wedge of suspensions, and really everything is, and you can make the argument precise, is built from this first vertex. So this is not true for the punctured cubes. They can store more information, but so we can choose a section to this evaluation here. And so this defines a functor, which we'll call ln by just composing this forgetful thing with this section S, which goes from C to Tn of C. And roughly what it does is it takes an object A, it extends it out to a cubical diagram like I drew. Just draw really quickly. You can think of these as the suspensions. So here we get a wedge of suspensions, and then forgets the initial vertex. So from A to this thing on the right. Okay, so now what Heist does is, and I guess I don't know what to call this, like a definition theorem, because I haven't told you what properties these things are supposed to satisfy. But you can iterate this functor ln to build the n-excisive approximations. So you can define this category P and C as the co-limit of doing this property over and over again. So from Tn of C to Tn of C. And this co-limit is the category P and C that has these nice properties. In fact, if your category is already, if your infinity category is already n-excisive, then this, you would expect that this map from C to Pn of C is an equivalence, but in fact, it stabilizes at the first step. So let's say C is n-excisive if and only if this map from C to Tn of C, which is Ln, is an equivalence. And so I've skipped over and black boxed almost everything in this section, but really I just want to introduce the construction of Pn of C through these cubical diagrams. Okay. So now I want to switch focus for a second and talk about cogroup objects. And so really what I need from this first section is this construction of Pn of C and this last proposition that I stated, that n-excisive functors or n-excisive categories have this property that this Ln map is an equivalence. Okay, so I want to talk about cogroup objects. So this is the dual to group objects. Instead of having a multiplication that takes a bunch of objects and gives you one object, it has a co-multiplication from C to Cn. So a particularly interesting example of cogroup object that is relevant to me is suspension objects. So I'll list this as a fact, is that suspension objects are cogroup objects. And maybe I'll say more specifically A infinity cogroup objects, because I will distinguish between different levels of homotopy coherence. So I guess one way of seeing this, if you take some suspension object and you can write it as a push out, it's like a wedge of 2 copies of 0 over A. I'm free to throw in another copy of A. And now I can pinch this middle copy of A to 0. But this is just a wedge of 2 suspensions. And so that map over here gives me my co-multiplication, and it's coherent up to all higher homotopies and et cetera, like this. And so now what you can do is we can consider the suspension functor as something that doesn't just go from C to C, but actually goes from C to, say, cogroup. I'll use this notation for A infinity cogroup objects in C. I can think of it as something that goes from C to cogroup infinity of C. If I have an A infinity cogroup object, so something that's very highly coherent, I can forget all the coherence up to or above level n, so I can extend along to just say, I'll use this notation as my shorthand for AN cogroup objects. So this is A infinity, this is AN. So by choosing which n I want to forget out, I can think of suspension as something that doesn't just go from C to C, but goes from C to cogroup, AN cogroup objects in C. Okay, so now if you'd like, you could, I don't know, just looking at what Heist does with this category Tn of C, you could iterate this process. So I could consider going from C, suspension functor, ending up in cogroup N of C, cogroup objects and cogroup objects of C, et cetera. If I call this co-limit of this thing, I don't know, Pn tilde of C, then I can build a little tower by just using the forgetful functors amongst the AN cogroup objects. And it turns out you have adjunctions here. And if I look at what's happening at the bottom level of this thing, this is just a co-limit of C goes to cogroup A1 cogroup objects in C. So an A1 cogroup object is just an object. So this is just the suspension, et cetera. And so this is really just the stabilization of C. I get this other tower that at the base looks like the stabilization, and who knows what the rest of it does. But it turns out that interestingly, this thing that I just did ad hoc out of cogroups ends up being the same as Heist's Goodwillie tower for infinity categories. So yeah, I'll state that as theorem. If I take C, my pointed compactly generated infinity category, then there is an equivalence from the category that I called PNC that I built out of those cubical diagrams to what I just called Pn tilde of C, which was just built from cogroup objects. So, and the way that this, so I think this is cool because this thing that I just called Pn of C, I just described a bunch of AN cogroup objects, whereas Pn of C is really built to look like a Goodwillie calculus object. And it turns out that these two constructions are equivalent. And the reason why this is actually is it turns out that these cubical diagrams that get used all the time in Goodwillie calculus actually give a model for AN cogroup objects in an infinity category. And so by proving that that thing gives a model, then in fact all these cubical diagrams that arise in Goodwillie calculus are actually diagrams involving cogroup objects. So that's what I want to do now, is kind of describe how this works. Maybe to do that, I need to introduce what I mean by cogroup objects more precisely. So I'll give a standard definition, for example, you can find in higher algebra, of what I mean by cogroup objects. So to give some more definitions, I'm going to let delta ing be the wide, so containing all the objects, subcategory of the simplex category of just the injections. And within that, I'm going to let delta sub n be the full subcategory of just the objects from 0 to n. So I'm looking at this truncated simplex category, and I've thrown away things that aren't injections. Okay. Now, if I want to talk about cogroups, the place to start is comonoids. So I'm going to let C again be pointed. Affinity category with, I guess, coproducts. And pointed here is important. It lets me throw away the injection or the surjections. And I'll define an AN comonoid in C is a functor from, so I'll call it A, from this delta N to C. So it's a truncated cosimplicial diagram. And it satisfies some properties. So this is going to look like the Siegel definition of A infinity monoid objects. So one, I require that when I evaluate A on the zero object, or sorry, on the object 0 in the simplex category, I get 0. And the second thing is I require some co-Siegel identities. So for each m less than n, I can take the collection of maps p sub k from 1 to m, which sends 0 to k minus 1 and 1 to k. And these induce an equivalence from the coproduct, k equals 1 to m, of A evaluated on 1 to AM. So this is the dual of the Siegel identities that say for a monoid object, A of M is equivalent to a product of A1s. So now I have here that A of M is this coproduct of A1s. And I also am going to require that my comonoid objects are co-unital. So the way that I do that is I specify that the following composites must be the identity on A evaluated at 1. So the composites look as follows. I can start with A at 1. I can use the simplicial map D1 to get to A of 2. My co-Siegel identities tell me that this is A of 1, coproduct A of 1. And so I can send one copy of this to 0. And I'm left with A1. And so I require that this is the identity. And then there's another composite where I send the other copy to 0. And so the idea is usually in a monoid object, you have to specify the unit, which would be like some map from 0 to A1. So since I'm specifying a co-unit, it's a map from A1 to 0. But because I've said that things are pointed, there's only one map from A1 to 0. And so co-unitality, I don't need to specify an actual co-unit object. There's only one map, and I instead just have to specify that these composites are the identity. The fact that I'm pointed also lets me get away with only having injections, because somehow the surjections and the simplicial identities tell you how this co-unit condition, I guess, propagates to like higher levels. Okay, so this is an AN comonoid. I think of it as a truncated cosimplicial object that satisfies these properties, co-Siegel property, etc. To make it into an AN cogroup, there are lots of ways. I'll choose the following definition. An AN cogroup. So here I'm trying to make the co-multiplication cogroup-like, is an AN comonoid A satisfying also the stronger condition 2 prime. So my original condition 2, this co-Siegel identities, I can make stronger as follows. I require for any m less than n and partition so any partition of the object M into 2 subsets that the square, so really to be precise, this should be at the cardinalities here. So this square just comes from thinking of a subset as a injection into M is a push out. So this is a stronger condition than the co-Siegel conditions. Instead of just requiring these specific maps PK, which break up my M into these M pieces, any way that I break up M out of order, I get a push out square like this. So if my comonoid satisfies this additional property, then I call it an AN cogroup, and it's cogroup-like. It's maybe worth remarking that cogroupness is really determined. It's just a property. It's determined already at the level of the homotopy category. So if I take my object, my AN cogroup, which is a diagram like this, then that's an AN cogroup if and only if when I push forward along the map to the homotopy category, I get a genuine cogroup. So it's really just some extra property that I'm asking for, that these squares are pushouts. I don't have to specify any extra data. Okay, so this is a standard model for working with comonoid objects. And my goal is to relate it to the cubical diagrams that appeared in the construction of PNC. So the first thing to note is that there is an isomorphism. Because I've thrown out all the surjections, if I look at my punctured n+1 cube, then this is really just the same as if I take delta n and I slice over the object n. So this comma category here, the objects are just injections into n. So those specify subsets. A subset gives an injection. And so I can think of this is just the power set. And so because of this, I have a really natural map that just forgets down to here. And so this gives me a map from this punctured cube to delta n, and I can pull back along that map. And if I do that, so that map, so this induced map, which I'll call pi n, which goes from functors from delta n to c, into functors from the cubical diagram, punctured cubical diagram, into C, then this actually restricts to a map on cogroup objects and the category of special punctured cubes. So it restricts to a map from AN cogroup objects in C to this category TNC of special punctured cubes. And so I have a direct relation between the two. So how does this work? Let's say I take the only case that I can ever draw, n equals 2. What is an AN cogroup object? It looks like a truncated diagram like this. where maybe I'll call these maps I0, it's the first inclusion, I1, and this middle map I'll call it M is the co-multiplication. And I say that this is a cogroup object, so it satisfies this condition 2 prime. So what I can do is I can take this and I can blow up this thing into a punctured cubical diagram. Surprisingly bad at drawing cubes, considering I've drawn 1,000 cubes. So I can blow this up into a cubical diagram like this, a punctured cubical diagram. And now this condition that I had here, this condition 2 prime, tells me that the faces of this cube are all pushouts. So for example, what do I have to do? I have to make a partition. So if I partition 2 into 0, 1 and 0, 2, then my condition 2 prime tells me that the square that goes from 0 to A, and it has an inclusion there, and this map M is a pushout. So for example, this back face is a pushout, and I could decompose into 0, 1 and 1, 2. That would tell me that the bottom face is a pushout. And 1, 2, 0, 2 would also tell me that the front face is a pushout. And so this pullback map just restricts to a map from cogroup N to Tn of C. And so I have this really, I think, nice way of saying how you can blow up a cosimplicial object into one of these punctured cubical diagrams. The interesting thing is that you can actually go backwards. So in fact, the functor pi n, when we've restricted to cogroup objects and Tn of C, is actually an equivalence. So given a punctured cubical diagram, you can actually extract one of these flattened cosimplicial diagrams. And so this is really the technical heart of everything, the thing that you have to show. The way that I do this is very technical and I think kind of not enlightening. So the formal way is I can look at the map from cogroup N of C to cogroup N minus 1 of C. And this is a fibration, and I can think, what additional data do I have to specify to an AN minus 1 cogroup to make it into an AN cogroup? So that defines a fiber of this map here. On the other hand, I can think about the fibration from Tn of C to Tn minus 1 of C and think about what additional data I have to add to a punctured N minus 1 cubical diagram to make it into an N cubical diagram. So for example, if I had a, I don't know, if n is 2 here, then I've just specified an object A, and I can, well, might not get into that very much. Actually, yeah, never mind. So I have these two things here, and I think about how I can add extra information. So I'm interested in the fiber over them. I can fill this out to a square here using my maps Pn, or pi n and pi n minus 1. And you can actually show that the fibers here are equivalent. There's some technical computation, and because the fibers are equivalent, this square is a pullback. And then I can prove by induction, if this one is an equivalence, then this one up here is also an equivalence. And so through induction, you can prove that this map pi n is always an equivalence. This is not very enlightening, so I'd like to do a more in-depth version for the case n equals 2 of how you might see how you could truncate, or how you could take this cubical diagram and flatten it into one of these cosimplicial objects. So I think this is kind of non-obvious. Let's say I take my cubical diagram, which I'll just on the fly make up some names for things. Cubes are so hard to draw. So here I have a special punctured cubical diagram. The first thing you'll notice is that the vertices I've labeled with different names, A, B, C, and D. Now, if I want to take that object and turn it into one of these flattened co-simplicial objects, well, there's only one thing here and one thing here. So first step would be to show that all of these vertices B, A, and C are actually equivalent, and that this cube is really built from one object here. So I can use the fact that these squares are pushouts to do this. Let's say I look at, say, this bottom square and this right face of my cube, and let's flatten that out to make it easier to see. Which one am I doing? C. So both of these faces here are pushouts. And so that means that the cofibers of all the vertical maps are equivalent. So if I take the cofiber here of this map from 0 to B, that's just B. Likewise over here, this is just C. I don't know what this cofiber is. It's something. But the point is now I get induced equivalences here and here. And so I get this chain of equivalences from B to C that tell me that B and C are equivalent. So maybe through some non-canonical zigzag. Now if I take, say, the front face and the same right face and lay those out. So from 0 to C to 0, C to D, 0 to B, 0 to A. So again, this told me that B and C are equivalent. Then by the same reasoning, so I have pushouts here, just looking at the other two faces. This tells me that B is equivalent to A. And so B, A, and C, all of these vertices that were a priori different, actually end up having non-canonical equivalences between them. And so really this entire thing now is trying to push these equivalences around in a coherent way to be able to flatten down to one of these co-simplicial objects. So what you can do is kind of, let's say I make these identifications, these equivalences, you can actually set things up so that your cubical diagram, and let's say I leave A as the object that I want. So I set this up where I have my same object everywhere. And what I can also do here is I can, so the bottom face is a push out of A and A. I can push all the equivalences to one corner, and I can make these bottom things coproduct inclusions. So D is just the coproduct of A and A again. But that leaves me with one interesting map here. So the idea is there's no room in this diagram to like push everything off. If you're going to make all of these identifications through these non-canonical equivalences, you have to push it off somewhere. And so you're always left with something that's interesting. So here I have some interesting map that's not just a coproduct inclusion. But now if I have this object like this, well, this is just what I had before, right? I can flatten this. I have my coproduct inclusions and some interesting map M here. And so this gives me one of these co-group, well, this gives me some object here that I can flatten into a co-simplicial object. I want to ask, is this object a comonoid? So does it satisfy these like co-unitality conditions, for example? And co-unitality conditions also come from the fact that every face here is a pushout. So for example, one of my co-unitality conditions I can state like this. If I look at the square from 0 to A to A to A wedge A, and here's M and I1, co-unitality here asks that if, say, the following composite, if I do M and then send one of the factors to 0, so here's a 0 map. So here I'm sending the first factor or the second factor to 0, then it asks that this composite here is the identity. So I'm just asking that the square commutes. And it does just because the square is a pushout. And so the idea is kind of like with no room to spare, the fact that all of these faces are pushouts just forces all of these identifications that we can make in very non-canonical, hard to deal with ways, which is why it takes a while to actually prove this theorem through this like weird calculation involving this fibers and induction. But you can kind of see how it works, at least I hope so, when you start trying to do it with like a n equals 2 cube. Maybe as a further example, if you say you had 2 of these cubes, so 0 to b, well, let me just do this. So here's one cube, and here's another one. And this one, I've made some identifications, and I have some object that I call B. And so here's some interesting map MA, and here's B, 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 B wedge B. So these are 2 special punctured cubes. And now I tell you that I have a map between them. Of course, a map between cosimplicial objects, well, under this identification, well, I guess a priori, I could have a bunch of different maps, say from here to here, here to here, and here to here. And I don't know any relation between them. So say they're F, G, and H, and there's some other map here, K. And of course, if this was a map of cogroups, I should expect that actually F, G, and H are all equal on these vertices. And you can do this through, again, the fact that all the faces are pushouts using things like this co-unitality condition. For example, if you were to take a square, A goes to B with F, and then here I can use my map MB and MA, and this commutes, and here's my map that I called K, and I have some, say G here, then by co-unitality, these composites here are the identity. And so this square commuting tells me that actually I have a commutative diagram that looks like this, where maybe I'm hiding some coherence things. And so in fact, F and G do the same thing on the vertices. By symmetry, you can show that H does the same thing, and then you can show that K is just a coproduct of F and F. And so really all of this stuff that a priori looks like different information is forced by these faces being pushouts to all be the same information. And so that's kind of, I think, the hopefully useful intuitive idea that goes behind this. But the upshot is that these cubical diagrams that come up all the time in Goodwillie calculus are just diagrams expressing that something is a cogroup or an AN cogroup. And so using this, you can actually see what certain results from Goodwillie calculus tell us about cogroups. So that'll be the third part. So for example, the following, I mentioned this way back when I was doing this Goodwillie calculus stuff. I mentioned this proposition here that a category is n-excisive if and only if this map is an equivalence. Well, now I can rephrase this in terms of cogroups and get away from this Goodwillie calculus stuff entirely. So as a corollary, I get that C is n-excisive, so it has these nice properties that Heiss lays out. If and only if the suspension functor from C thought of as landing in AN cogroup objects in C is an equivalence. And so just by interpreting these cubical diagrams in this proposition of Heiss from earlier, we get this statement. And this statement I think of as a kind of desuspension result. So this being an equivalence says that if I start with a cogroup object here in C, an AN cogroup object, then in fact I can realize it as the cogroup structure that canonically comes with the suspension of some object in C. And so I interpret this as saying something like in an n-excisive infinity category, every AN cogroup object can be desuspended. And so this is kind of the, this kind of desuspension result brings to mind this sort of dual, like a classical dual picture about delooping group objects, right? So if I have an A infinity group object, then I can deloop it and I can witness it as just a loop group on some other object. So this is sort of the dual picture thinking about desuspension objects. And so what this result says is that if my infinity category is n-excisive, then I don't need a whole A infinity cogroup structure to do a desuspension. In fact, I only need the coherence information up to level n. So now what you can do in like classical Goodwillie calculus manner is you can try to work your way up the tower. So really, I don't care about the levels of this Goodwillie tower. I want to know what it tells me about the original category that I'm interested in. And so you can immediately formally extend this to a result at the limit of the tower. So again, if I let P infinity of C, C is my pointed compactly generated infinity category. So if I let P infinity of C just be the limit of the tower, then I get an A infinity desuspension result. So the suspension functor from P infinity of C to A infinity cogroups in P infinity of C is an equivalence. And so this is pretty formal. What I'm doing is just, I can take P infinity of C, which is the limit of some tower. I have these relations that I proved are equivalences from this corollary here to say, so this is cogroups 3 and P3 of C, cogroups A2 cogroups in P2 of C, and A1 cogroups in P1 of C. And at each stage of this tower, this is an equivalence. And it turns out that you can prove that if you take the limit of this right-hand tower, what you get is A infinity cogroups and P infinity of C. So you can raise the n on the right-hand side together. And so this map here is a equivalence, and it turns out to be the suspension functor on P infinity of C. And so the idea is, by just examining how cogroups work with these cubical diagrams, we can get this corollary statement, which tells us something about Pn of C, the excisive approximation to our category. We want to recover something about the category itself. So we work our way up the tower and we get this desuspension result for the limit of the tower. And now the idea is, this is very general. If I know something specific about the category C that I'm interested in, I can try to use this to recover something about the original category. So for example, Heist tells us that the Goodwillie tower converges for simply connected spaces. So there's an equivalence from pointed simply connected spaces to P infinity of pointed simply connected spaces. And so now using this, I can try to transform this into a desuspension result about actual topological spaces, not just a result about Goodwillie calculus. So the statement that you can get out of this is originally a theorem of Klein-Schwanzel-Vlach, which says that, maybe to paraphrase, the suspension functor induces an equivalence from simply connected spaces to I guess this is two connected infinity cogroups. So this is the kind of result that you would actually like. So this is the best undisputed dual to the famous result that you can deloop A infinity group objects. So you can desuspend A infinity cogroup objects as long as they're two connected. At best, you would hope one connectedness, because the suspension will raise the connectedness. And so you can prove this really easily. Well, easily. I would say you can repackage the proof that Klein's functional evolve could do that they note uses a lot of these cubical diagrams that come up in Goodwillie calculus, but it's just missing this like explicit relation between the two. You can repackage this just into a nice square diagram here. So I changed my notation. Call this topological spaces. So top star for pointed spaces. So the map that I care about is this map from simply connected spaces to two connected cogroups. Okay, that's the map that I care about. Now, Hayes tells me that this converges, the Goodwillie tower for simply connected topological spaces converges. So there's an equivalence like this. And by applying cogroup infinity as a functor to that equivalence, I get an equivalence down here. And now this general result that I had before about this desuspension result for the limit of the Goodwillie tower tells me that this is an equivalence here. And so therefore I must have that this suspension functor here, where here is an equivalence. And so I think this is really nice. Basically what it does is repackage this proof of these three authors into this really two parts. So there's this general statement here about a desuspension result for the limit of the Goodwillie tower. And then there's specific work that you have to do for the category of interest. And then because of this, you get that this left-hand side is an equivalence. So you can really see how this proof breaks down into these two parts when they're packaged this way. I think it's also cool because, again, this right-hand thing is very general. So if you can prove the specific thing that you care about up here, then maybe you can apply this to different things in spaces, anywhere that you know something about the convergence of the Goodwillie tower. Maybe I should say that maybe I should say that really the most general thing that you could hope for here is that on the right-hand side here, you have one connected cogroups, and on the left-hand side, you just have spaces. And so I'm unable to recover that in this case because I don't know anything about the convergence of the Goodwillie tower for spaces in general. So yeah, I don't know how much I want to get into that. But you get this one suspended level up just because we know something about the convergence of the Goodwillie tower for simply connected spaces. Yeah, maybe it's a place to stop. I think I spoke a lot faster than intended.
All right, well, that leaves time for questions. So any questions?
Hey, I have a question.
Yeah.
Yeah, I mean, first of all, I really like the result. Nice talk. But I'm wondering, like, you write down this inverse limit of the nth approximations, and you argue that this is equivalent to core group objects in it.
Mm-hmm.
Somehow it seems to me, I mean, could also just take the co-limit over A infinity core group objects, and that probably has a universal property. Is that right? I mean,
so this is on.
I guess my question is, yes.
Yeah, I mean, there's.
Right, exactly. Like
right. So I mean, I'm secretly.
And somehow this.
Yeah, like there's. I mean, it's probably not as straightforward as just writing this down. You need to know. On the one hand, you can build cogroup or A infinity cogroups as a limit of A n cogroups. You need to know how cogroup objects look like in the limit of a tower of infinity categories in general. So it's not obvious that those look like the correct thing here. So there's like a little more that goes into this. But I guess what you're saying, the co-limit of something?
No, I was saying like you could just contemplate the universal thing universal category under C in which, I mean, which is equivalent to its co-groups, like which makes suspension an equivalence?
Yes,
And
so
probably just the co-limit over the diagram where you go from C to A infinity co-groups in C and then iterate this construction.
right, so you can do this and you actually, right, what you're saying is kind of like, so in the stabilization, I try to force the suspension to be an equivalence. And if you look at this construction of Heist for Tn of C and replace Tn of C with cogroup, then what I'm doing there is forcing the suspension to be an equivalence, not from C to C, but from C to AN cogroups. So you can try to force the suspension to be an equivalence from C to A infinity cogroups in C. But I think in general, this is something that I tried to prove is the same construction. And I couldn't prove that this gives you the same thing. So there's like a canonical comparison map between them. But yeah, I talk about this in my archive preprint a little bit, but I don't know if it's true, but I just wasn't able to see that you could
right.
get...
I mean, I read this part of your preprint. I guess my question was a little bit more basic. I mean, first of all, is it true that this co-limit is just the universal thing where you turn suspension into an equivalence? Or do we have to iterate this co-limit?
I guess, wait, maybe we're talking about different things. So I'm saying, so if you take this thing and go to, say, A infinity cogroups and C, and then just keep doing this, right?
Right.
Then, and you take this co-limit, you get something I'll call. Yeah, so that's what I say is like you get something, I call it, would give it a useless name. And in general, there's a map, I think, from P infinity of C to this thing, but I'm not sure that it's an equivalence.
I mean, shouldn't the map go the other way?
I
mean, I guess it's an adjunction. But I guess, I mean, I was asking if this P infinity tilde C, is this a universal, I mean, does this have a universal property? Is this a thing where you turn suspension into an equivalence or not?
Okay, yeah, I haven't really looked into it, but I would imagine so. It should have this, right. I mean, yeah, right, okay.
Not entirely clear whether for this category also it holds that this category is equivalent to co-groups in this category.
Right. Yeah, I don't know. There's like tricky stuff that happens at the limit of these towers where they don't have the, like.
Yeah, but anyways, maybe we shouldn't go on forever here. Maybe other people want to ask questions as well. Sorry.
Any other questions?
So have you tried to do that with any other example, which is not like a Hodge example? Instead of like topological space, connected topological spaces, local spaces with respect to any particular spectrum or?
No, I haven't tried to do this. I think like, I don't know, secretly I'm more of a like category theory person than a topologist. And so I think like I miss a lot of the specific knowledge. But yeah, I would like, you should get some kind of result for, and this is what I was like saying here, in any case where you can say something about the convergence of this tower, you should get some kind of result. So, and I'm not sure what those results look like in general. Like, I don't know what, say, co-group objects in like algebras for an operad look like, for example. Maybe there's interesting things you can say there.
Yeah, but have you worked out other examples? I mean, non-topological, just categorical, or?
No, I haven't looked at the specific examples. Yeah, I guess maybe like, I don't know, the last thing that I was gonna say is, so you can, I worked for a little bit to try to, I guess, lower the connectedness in this statement here. So you would like to say something that there's an equivalence from, say, topological spaces in general, or maybe not an equivalence, but even fully faithfulness to infinity cogroup objects in, say, one connected spaces. So this is the best result you would hope for. And so if you tried to do this kind of square argument again, you need to know something on the top of the square between, you need to know how to relate topological spaces to, the tower on topological spaces. And this in general is not an equivalence. I don't know what you can say about this. You can look at the subcategory of topological spaces for all spaces who converge to the limit of the Goodwillie tower of the identity. So if I call those like top con for convergence, then you get a fully faithful functor here. And so completing out the square, you'll get a fully faithful functor down here to this one connected thing. And then, I mean, it's just like everywhere else, you just have these. Here you get an equivalence to cogroup infinity, P infinity top from that result that I mentioned. But in general, like the best case scenario here for one connected spaces, I don't know that this would be an equivalence. So if you remove conv here, there's like a paper of Mike Hopkins where he claims that this is an equivalence, or not an equivalence, fully faithful. These three authors try to prove this result and aren't able to do better, or aren't able to recover Mike Hopkins' result. But that could be because they are secretly using these Goodwillie calculus methods. And so they're running into problems at the convergence of the tower. So yeah, there's just a lot of convergence issues at the boundary of where Goodwillie calculus works and fails is very complicated. And so you can't recover this stronger result without maybe recovering the more interesting, stronger result about the convergence of the tower in general.
Okay, thanks.
Any more questions, anyone? All right, if not, I guess we'll break, but let's thank Daniel for his beautiful talk. I thought it was a fascinating talk.
Thanks.
So thank you.